Hi, welcome to chapter 3 of our course on DC circuits and electromagnetic induction. I hope you have learned important concepts in the previous chapters. If not, head over and watch it first. So, in chapter 3, we learn about self-inductance, mutual inductance, coils in series and parallel, energy stored in the magnetic field, and solve few numerical problems. This chapter is the application of the concepts you have already learned in chapter 2. So, let's begin. There are two types of EMF: statically induced EMF and dynamically induced EMF. Statically induced EMF is produced by keeping both the magnet and coil stationary and passing an alternating current through the coil, while the dynamically induced EMF is produced by the relative motion between the magnetic field and the conductor. Now we'll focus on statically induced EMF. Again, there are two types of statically induced EMF: self-induced and mutually induced. Let's look at self-induced EMF. The self-induced EMF, it is the electromotive force induced in the coil due to the change of its own flux. To understand this, consider a coil having n number of turns. It is connected to an alternating current power source. Whenever the AC current flows through the coil, it will set up a varying magnetic flux in the coil, as we can see. So, what happens after this? According to Faraday's law, if there is a change in magnetic field linking with the coil, an EMF will be produced in that coil. So, the coil is capable of producing its own EMF. That's why we call it as a self-induced EMF. The nature of this electromotive force or the voltage is opposite to the cause producing it. Hence, the direction of this EMF will be in the opposite direction of the AC current. This is according to Lenz's law, which tells us the EMF and hence the current in the conductor is such that it opposes the cause producing it. Now we will look at the mathematical expression for self-induced EMF. It is given as E proportional to di by dt. The induced EMF E is directly proportional to the rate of change of current as we saw earlier. By adding a proportionality constant L, we will have E equals minus L di by dt. Here, L is the coefficient of self-inductance and is measured in Henry. The coefficient of self-inductance is defined as Weber turns per ampere, or simply put, it is the number of flux lines linking with the number of turns of coil for a given current. We denote flux as phi measured in Webers. Number of turns in the coil is given by N and current as I measured in amperes. Therefore, we have L equals phi into N by I, Henry. Now, it's time to recollect the definition of self-induced EMF. It's the EMF induced in the coil due to the change of its own flux linking with it. So, that's about self-inductance. To sum up, in this video, we learnt about types of statically induced EMF, self-induced EMF, coefficient of self-inductance, and its formulas. In the next video, we will go through another type of statically induced EMF, that is mutually induced.